Okay, so question number 26 on page 655 is asking you to find the total electric field at point C from being caused by the charge at A and the charge at B. So our first step is to find the electric field from A at C, and we just totally ignore B. So we do KQA over R squared, so 9 times 10 to the 9th Newton meters squared per coulomb squared. QA is 46 microcoulombs, so 46 times 10 to the negative 6. And the R is the square root of 0.0041 meters, and that gets squared. Okay, so it's not just 41 because we had to change it to meters, right? And when you do this, you get EAC to be 1.00976 times 10 to the 8th newtons per coulomb. Now we're going to totally ignore A and find the electric field strength from B at C. So 9 times 10 to the 9th Newton meters squared per coulomb squared. QB is 82 times 10 to the negative 6 coulombs. And it's divided by 0.04 meters squared. And you get an E at C from B of 4.6125 times 10 to the 8th newtons per coulomb. So we have our field strength from A at C and our field strength from B at C. So we now have to add them up, but they're vectors, so we have to take into account their directions. So I'm going to redraw C down here. And I'm going to look and say, okay, what's A doing? What's the field from A doing at B? Well, A is positive, so its field is going out in all directions, right? Which means along the line that's connecting A to C, the field is going out. So up here it'd be going this way, and I'm just going to draw it here so I'll have more room. So this is EAC, the 1.00976 times 10 to the 8th newtons per coulomb. What is B doing at C? Well, B is also positive, so the field lines around B are also going out in all directions, and so at C it would be going upward. So here it would be doing this. So this will be EB, which is 4.6125 times 10 to the 8th newtons per coulomb. Okay, so before we add these together, we have to find the components of the field from A. So it's going to have a component in the X direction and a component in the Y direction. Okay, and this angle will be this angle. So 38.66. And just to clarify that, right, because here's your EA up here. You break it into its components. These are similar triangles, corresponding angles. Okay, so the Y component is going to be the sine. So it's going to be 1.00976 times 10 to the 8th newtons per coulomb sine of 38.66. And your X component will be 1.007976 times 10 to the 8th newtons per coulomb cos of 38.66. Type these into your calculator. Y should be 6.308 times 10 to the 7th newtons per coulomb, and your X should be 7.8849 times 10 to the 7th newtons per coulomb. All right, so once you have these, now you can do sum of the fields. So sum of the fields in the X is easy because there's only one. 7.8849. Is it just me or is that blurry? Times 10 to the 7th newtons per coulomb. So that's my total field in the X. My total field in the Y, they're both going up, so I'm going to add them. So it'll be my 6.308 times 10 to the 7th newtons per coulomb plus my 4.6. 125 times 10 to the 8th newtons per coulomb. And so I will get a total field in the Y to be 5.2433 times 10 to the 8th newtons per coulomb. And that'll be up. So once I get my two totals, this was to the right, now I redraw my diagram. So I have a field to the right of a component to the right, 7.8849 to the 7th newtons per coulomb, and then I have one going up that's significantly bigger, 5.2433 to the 8th. This should really be, the x should be a lot shorter than the y because one's to the 7th and one's to the 8th. So this will be my E at C, and this will be my theta. So square them, add them together, and take the square root. You should get 5.302 times 10 to the 8th newtons per coulomb at an angle of 81.45 degrees. And if you look, that's counterclockwise to the positive x. The final answer to number 26. Now the good news, the other one I gave you was number 29, and it is easier. Okay, it's easier because it's in a straight line. 2-point charges of negative 40 microcoulombs and positive 50 microcoulombs are placed 12 centimeters apart in the air. So 40, 50. This one's the negative. And this distance between them is 12 centimeters. And the question wants to know at what is the electric field intensity midway? So here at this point, so this will be 6 centimeters and this will be 6 centimeters. What's the electric field intensity here? So first step, find, we'll call this one number 1, this one number 2. So find E1, and it'll be equal to KQ1 over R squared. 9 times 10 to the 9th Newton meters squared per coulomb squared. Negative 40 times 10 to the negative 6 coulombs over 0.06 meters squared. Then do E2, KQ2 over R squared. 9 times 10 to the 9th Newton meters squared per coulomb squared. Positive 50 to the negative 6 coulombs over 0.06 meters squared again. All right, so for E1, you should get negative 1.00. 636, yeah, you do, times 10 to the 8th newtons per coulomb. And for E2, you should get 4536, 1.25 times 10 to the 8th newtons per coulomb. So we have our two E's. Now, and one's positive and one's negative, but remember, the negative's just telling us which way it's going. So E1, what is E1 doing at this point? Well, number 1 is a negative charge, and in negative charges, the field lines are going in, right? They're going into number 1. So right here, this field, E1, then, is really 1.00 times 10 to the 8th newtons per coulomb, and it's going in the direction I have drawn here. How about E2? What's it doing? Well, it's a positive charge, and around a positive charge, the field's going out. So at this point, E2 is acting like this, 1.25 times 10 to the 8th newtons per coulomb. So what do you do to get the total field? Well, look, they're both going in the same direction. E total, you're going to add them. So don't get fooled by this minus sign and don't think you're going to subtract them. The minus sign is telling you which way that particular vector is going. And once you have the vectors drawn, the drawing tells you, oh, I need to add them. So 2.25 times 10 to the 8th newtons per coulomb, final answer. Okay? Very good.